Welcome to the Chapter 3 lecture for the Management 3120 Operations Management course. I am Dr. Bill Perkins, and I'm going to provide you a video lecture based on the material found in the textbook Practical Operations Management, 2nd edition from Natalie Simpson and Philip Hancock. Our objectives for this chapter is to be able to define quality, investigate quality, and to develop product designs. So let's get started. Products are described by design specifications, such as those of the 2-pin audio adapter seen here and also found on page 67 of your textbook. When this particular adapter is measured and is found to match the specifications, it is said to have satisfactory quality of conformance. So remember that, quality of conformance. And quality of conformance is the degree to which the output of an operation meets the producer's expectations. Now, quality of conformance requires a product to conform to the producer's specifications, but this conformance does not guarantee that the product will be a success. So the success of a commercial product requires that customers actually purchase it. All right, what good would a product be if people didn't buy it for an organization? Furthermore, the broader issue of value creation for any kind of product cannot be confirmed if, in fact, that product is never consumed. So while this disconnect between satisfactory quality of conformance and actual value creation has always existed, it did not gain widespread attention until the 1980s, when a series of complex commercial products conforming to manufacturers' expectations failed to remain competitive. Now, this clarified the idea of quality of design, or measuring quality in terms of the degree to which a product meets the customer's expectations. So if a product meets or exceeds a customer's expectations, it has satisfactory or excellent quality of design. Now remember, the degree to which output of an operation meets the customer's expectations is the actual definition of quality of design. Now, a history of product quality begins with quality of conformance, the start of which can be argued back centuries. However, scientific methods for inspection and monitoring would not be widely recognized into the 1920s, starting with the work of Walter Schuhart at Bell Laboratories, so known collectively as the Statistical Process Control, which is the SPC for the acronym, or the initials, abbreviation, whatever you want to call it. These tools remain in active use today, and one of the most widely recognized, the control chart, is sometimes called the Schuhart chart in honor of its origin. So the concepts of quality of design and continuous improvement followed decades after the development of the SPC, the Statistical Process Control. So implementing these concepts required companies to broaden the types of activities taking place within their respective quality management programs. Now, beginning on the left with the SPC, figure 3.2, illustrates several well-known quality programs that emerged during this time period, which offering guidance on how to pursue quality across multiple dimensions at once. Now, modern quality management promotes the idea of process ownership, where employees who staff a process also monitor and manage its performance. Now, traditionally, these services were provided by a separate team of skilled inspector and engineers, such as those pictured here, often referred to as Quality Control Department. However, promoting process ownership among employees usually does not mean that the QC, or the, sometimes you'll hear of it as the QA department, disappears. as the reality of production may not leave enough time for workers to complete all inspections, and or some monitoring may require specialized skills and equipment that just aren't present at the moment. So the word total in the phrase of total quality management emphasizes that the three different dimensions of quality discussed at the opening of this chapter are pursued simultaneously in an integrated effort. The 1980s often cited as the period in which the concept of total quality management, which is also referenced as TQM throughout the chapter and the remaining portion of the textbook, it first gained widespread recognition and adoption, particularly here in the United States. Although many components of total quality management have a much longer history, in fact, TQM programs often feature the age-old tools and concepts of quality of conformance, but they expand and improve them by integrating additional tools and concepts that address the vulnerabilities of the older viewpoint. So, unlike TQM, whose exact origin is unclear, the modern philosophy of lean operation can be traced to the Toyota production systems, also known as TPS, a holistic management program developed around Toyota's early innovations in the just-in-time, which will also be referenced as JIT production. Now, this stream of evolving programs introduced the concept of MUDA, a unifying term for anything the customer is not willing to pay for. So in avoiding MUDA, and you'll see it's spelled M-U-D-A, a lean system occupies the intersection of quality of design and quality of conformance, as a customer is only willing to pay for a product that meets his or her expectations, right? Makes sense. So lean means operating without waste, and MUDA is a Japanese term for waste, particularly anything the customer is not willing to pay for. Now, some of the most widely recognized credentials in quality management are key components of Six Sigma, a data-intensive program first developed by Motorola in the 1980s and now operational in thousands of organizations around the world. Six Sigma features the certification of individuals in particular, providing, now remember, it's not going to be organizations, it's going to be more personal based, individual based. It provides a formal regimen of training to earn distinct designations such as Green Belt or Black Belt in Six Sigma. So these individuals then use this training as members and leaders of cross-functional teams that pursue continuous improvement through a series of projects. Now, each project is completed with careful attention to Six Sigma's signature DMAIC cycle of activity. I'm going to say that again, DMAIC cycle of activity, which is an abbreviation for define, measure, analyze, improve, and control. Now, interestingly, the term Six Sigma appeared around the year 2000, as some companies began integrating Lean's version of a responsive operation without waste with Six Sigma's structured methods for problem solving and continuous improvement. Now, some experts debate whether merging these two approaches is beneficial, while others dispute whether they were or ever significantly different in the first place. But the concept of Lean Six Sigma nonetheless remains popular in the industry today, particularly in large manufacturing firms. Again, Six Sigma's signature DMAIC cycle of activity is an abbreviation for define, measure, analyze, improve, and control. So perhaps the most powerful feature common to modern quality programs is devotion to continuous process improvement. Traditionally, quality control treats the issue of quality as a state to be maintained, through pursuit of some ideal amount of inspection. So modern quality management not only shifts the responsibility for quality away from the group of inspectors, but it also transforms the perception of improvement from an unrelated issue to an everyday activity. Now, lean operation contributes to the term Kaizen, the Japanese word for improvement, as a name for this commitment. However, it is Six Sigma that offers the most detailed advice on how to accomplish this, including project selection process and a separate parallel organization structure in which Six Sigma teams work. The Six Sigma teams work on assigned projects championed by senior management, employing that DMAIC methodology I spoke about in the previous slide. So the restless nature of continuous improvement creates the need for an investigative analysis to identify opportunities for improvement. Now, Total Quality Management, TQM, promotes a vision of everyone in the organization supporting the mission to some degree, recommending the creation of quality circles, or groups of employees who meet regularly to identify opportunities and develop solutions. So to be effective, quality circle members are trained in the use of a variety of problem-solving tools that are otherwise not common in traditional quality control programs. So remember, a quality circle is a group of employees that meet regularly to discuss and develop opportunities for continuous improvement of an operation. And the Pareto analysis offers a structured method for detecting and prioritizing potential opportunities for quality improvement. It's named in honor of the 19th century Italian economist Wilfredo Pareto. Kind of rhymes. This style of analysis begins by gathering data on the frequency of occurrences believed to contribute to some issue targeted for improvement. So, this style of analysis again begins by gathering the data on the frequency of occurrence believed to contribute to some issue targeted for improvement. So the Pareto analysis is the use of statistics to identify the factors most influential in a particular outcome of interest. So the observations made during Pareto analysis can first be organized into a histogram, like the one here in figure 3.3 from page 73 in the textbook. Now the histogram in figure 3.3, the histogram is essentially a bar chart illustrating the relative frequency of occurrences in different categories. This one here suggests a frequency of various causes in delayed treatment by a hospital emergency room. Pareto analysis requires that these factors then are sorted by frequency and restated as a percent of total occurrence, as in figure 3.4 on this slide. So the purpose of Pareto analysis is to highlight any pattern of a critical few and a trivial many that Wilfredo Pareto first observed centuries ago. So while in a quality circle working on a project, illustrated in figures 3.3 and 3.4, identified 9 different causes of delay in drug treatment. Now, Pareto analysis reveals that the 3 of those causes account for 77% of all delays, and one particular cause, which was a busy CT scanner, is responsible for over 1/3 of those delays alone. So the quality circle can now tighten its focus, perhaps recommending rental or purchase of an additional CT scanner, or additional staff to draw and test blood, which was another major delay of the emergency room. Now, emphasis on the pursuit of improvement requires identification of root causes. Causal modeling focuses on apparent relationships among elements of a system or situation, often by reviewing data for patterns that might predict some issue of interest. So causal modeling is predicting an outcome by identifying its relationship with one or more factors. Now, if the data for causal modeling is available, a scatter diagram can highlight possible relationships between two issues, as seen here in Figure 3.5. So in Figure 3.5, for example, we see a greater number of errors in online reports strongly associated with higher numbers of hours at work before a report entry. And although the clustering of data points in Figure 3.5 suggests that online reports entered later in the work shift are less accurate, this relationship can be clarified further by calculating the correlation coefficient for the underlying data. So correlation coefficients are broadly useful in any situation in which a linear relationship is suspected between any two issues under investigation. And correlation coefficient, again, is a measure of the strength of any linear relationship between two sets of observations. So for any set of paired readings, x and y, where n is the number of paired observations, the correlation coefficient, which is r, can be calculated with this formula. And the resulting value of r will range between 1 and -1, and a value close to either limit indicates a strong linear relationship in the data. So in contrast, a value near 0, the center of the range, indicates no linear relationship within the data. And Figure 3.5 here includes the correlation coefficient of the data plotted in a diagram, confirming a strong positive relationship of R equals 0.909. So while this does not prove that one issue is causing the other issue, it does, however, suggest that anyone interested in improving the accuracy of online reporting should begin by exploring options to move this activity as early as possible in a work shift and or investigate the conditions at the end of the shift for more detailed understanding of the root causes of inaccuracy, such as maybe employee fatigue. Calculating a correlation coefficient requires finding the values of the various summary statistics in the correlation equations. And we'll cover more of these calculations in the chapter scenarios as we move forward. I will also post other support videos that will kind of help you throughout these, making these calculations. Now, one difficulty in causal modeling, as discussed so far, is that it requires the investigator to suspect a particular cause and effect relationship and to possess numerical data describing that relationship. So in reality, causal modeling can be complicated by a lack of convenient data, and one issue under study may in fact result from many different causes, and not all those causes may be known by a single investigator. So causes themselves can have causes and may interact with other causes when contributing to an outcome, further obscuring the true issue of the root cause of the problem. Now, quality circles and employee involvement can be particularly helpful in such cases, in that a group of people directly involved with a complex process are more likely to succeed in its investigation by drawing on their combined individual experiences. Now, because TQM often relies on groups of people, brainstorming techniques are common in quality circles when working on such issues. Affinity diagramming also is pretty popular, but one tool particularly helpful to brainstorming a complex causal model is the fishbone diagram, like the one seen here in Figure 3.6. And I'm going to leave this up for a little bit for you to look at. Okay, moving on. So brainstorming among employees is a powerful process that requires more than great ideas for success. So visible in this picture of is a quality circle is the open meeting space needed to share documents and ideas, so all participants may view the contributors easily. Not visible, but more vital, is the requirement that each of these quality circle members be released from their um, unusual duties to participate in this meeting. So, organizations have to give up a lot for quality circles because essentially you're taking their members, and these are quality members, have be selected on such a problem-solving group, to take them away from their day-to-day duties and allow them to cross-functionally collaborate and brainstorm and come up with great answers, whether they're using a 5 why analysis, fishbone diagram, affinity diagramming. There's numerous tools these quality circles use, but organizations do need to strategize, backfill on when these individuals are released to go perform their quality circle. Although their respective areas may suffer a little bit with that being released to the quality circle, it pays dividends, down the line when there's a reduction in waste. There's less failures, there's more problem solving, there's more continuous improvement. Whereas Six Sigma is one of the best known quality related certifications, I was specific when I covered Six Sigma to emphasize that it's for individuals. However, ISO 9000 is one of the best known certifications for whole organizations, requiring audits to certify a business follows minimum acceptable practices in quality control, inspection, managerial responsibility, and continuous improvement. That continuous improvement keeps coming up throughout the chapter, so pay attention. Now, ISO 9000 is a certification of compliance with an internationally recognized set of quality management standards. And then we have benchmarking, and that is an important element in any quality management program, particularly in the quest for continuous improvement. And benchmarking requires an organization to identify companies that represent either the standards the organization wishes to maintain or the kind of operation that the organization aspires to become. So benchmarking is measuring performance relative to some peers' performance, generally identified as best in class. Now, one common mistake in product development is to assume that more design features create a more competitive product. Now, successful companies such as Apple have repeatedly demonstrated the power of less is more in product design. I know you've heard me say that in class, covering previous chapters. Do more with less. Less is more. But this principle is not as simple as it sounds. So its difficulty lies in discovering precisely how a product's potential technical features and the customer's perceptions of that product relate. So to overcome this difficulty, a company must bridge the gap between the two differing perspectives on product quality. So quality as a conformance and quality as a customer perception and expectation. So the quality function deployment, the QFD, it'll be known as QFD. I'm going to hit you with a lot of acronyms, abbreviations, throughout this course. So analysis, the QFD analysis provides a structured format for bridging this gap, mapping key relations between customers and the product developer's viewpoint. Now, the signature shape of a finished QFD model gives its nickname House of Quality, as shown in the following slides that I'm going to cover. So QFD entails modeling the mathematical correlations between customers' perception of a product and its technical design specifications. Now, first, the QFD analysis requires the voice of the customer to be captured in consumer surveys and focus groups, outlining what does the customer consider valuable in a product. Now, these customer attributes are listed in the left-hand side of the QFD diagram and are expected to be in the customer's own words, such as a desire for brightness or friendliness. In some cases, not all attributes are equally valuable to the customer, such as it is more important to be accurate than to be quick. And such preferences can be documented on a weighted scale directly to the right of the attributes. Now next, the product developers must identify what aspects of the product's design are in fact flexible and thus open to new design choices. That's that agility I was talking about in previous lectures. Now, these technical specifications are listed across the diagram, the top of the diagram, and the roof of the house of quality is formed by a table in which to mark any links or synergies between specifications. Now, once this house-shaped framework of the QFD analysis is established, further mapping of customer attributes to technical specifications requires the collection of two sets of data from two different groups of experts. Now, one data set is the result of presenting a group of customers with several different examples of the product, asking them to rate each brand according to the customer attributes. So the second data set results from evaluating the technical specifications of those same example products as measured by product design experts. So neither of these data sets appears in figure 3.7 here, but the relationship matrix in the diagram summaries it summarizes the correlations between each attribute's data and the data for each technical specification. So sustainability of future production and minimization of environmental impact both begin with product development. Although this has not always been the case, even when practicing conservation of raw materials such as oil and fresh water, organizations have traditionally used the cradle-to-gate planning approach. That's cradle-to-gate, which is focusing on sustainability from the procurement of a resource until its transformation into a product. So again, cradle-to-gate involves planning sustainability from the procurement of raw materials through the production of a product. Now, environmental problems and rapid changes in some technology have motivated a more modern cradle-to-grave, that's cradle-to-grave approach, requiring developers to begin with the end in mind and design for an eventual disposal of products as well as their use. So cradle-to-grave thinking does not necessarily include recycling, in that the grave for a customer product could be a landfill, although a cradle-to-grave designer would then specify biodegradable materials for the product so that it might break down faster and make better use of that landfill space. So the cradle-to-grave involves planning sustainability from the procurement on raw materials through the final disposal of the product. And the ideal in product development is a cradle. So the ideal in product development is a cradle-to-cradle design. That is the ideal design. Now, cradle-to-cradle, which plans explicitly for how a discarded product will be transformed back into something of value. This includes designing such that valuable materials are easily recovered for recycling, organic matter if free from chemicals that would prevent its purposing into fertilizer or animal food or entire sub-assemblies or finished products that can be easily decommissioned at the end of their lifestyle and adapted to alternative use. Okay, so that cradle to cradle is it's kind of recycling it back to use. So the ultimate achievement in cradle to cradle design is remanufacturing, a process in which old products are simply made new again to begin another lifestyle. So in practice, these are usually products that require a large investment in materials from the start, such as engines and other heavy machinery. So now we're going to go into our chapter summary, what we already had talked about. So we spoke about quality management can be traced back to over 1,000 years, as early craftsmen developed the standards of their trades and taught those standards to others. It evolved further into concepts of inspection for conformance, sampling, and statistical process control. Now, conformance to standards and specifications continues to this day as an intuitive and relevant definition of quality. Now, whereas a more traditional approach to quality would focus on inspection and conformance, a modern quality management program integrates these issues with additional concerns. Principally, programs such as Total Quality Management, remember it's TQM, and Six Sigma recognize that specifications being used to judge conformance must reflect the customer's expectations, not simply the good judgment on the producer. So recognizing the voice of the customer introduces greater complexity in that the customer brings both the issues of expectation and perception in the discussion of a product's quality, and the customer's perceptions of intangible products can be particularly surprising to the unwary provider. Now, modern quality management frames quality as a quest for continual improvement as opposed to simply a desired steady state. Now, because the program never stops investigating new opportunities to increase product quality, employees must be trained in the use of a variety of diagnostic and problem-solving tools such as Pareto analysis, fishbone diagrams, and benchmarking. Now, ultimately, quality requires the involvement of the entire organization to keep it developing in a positive direction, and leadership is critical to maintain this momentum. Essentially, what I want you to take away from this is that quality is a cultural thing. It does involve the entire organization. It needs to be shifted to more of a mindset and not just a bunch of required processes or competencies. So it is difficult to separate the exploration of product quality from the process of development. A product cannot be designed without the customer's voice, and continuous improvement encourages constant work towards improvement of that design. So companies may get design ideas from a wide variety of sources, but nonetheless, they need to develop them into designs with some mapping of their technical abilities back to the customer's desires using tools such as quality functions development or quality functions deployment. Ideally, the processes to be used in the future production of the design are developed concurrently with the product design activity. Now, for better efficiency, flexibility, sustainability, and safety, that's how it needs to happen. And that concludes our Chapter 3 lecture. Please tune in to Blackboard for this week's expectations and deliverables, and I will see you all in Chapter 4.